So we're going to look at the integral test. And the integral test, just like some of the tests we've looked at before, can tell convergence or divergence, but it doesn't give you the sum. So we have to do other things to find the sum. So like there are some convergent series where we can find the sum, like the geometric series. When it's convergent, we know it's convergent, and we can also find the sum using a formula. Or the telescoping series, where we can cancel out the same values in the middle and we can find the sum. But these, we're just telling whether it's convergent or divergent. We do not have to find the sum. All right, so the integrals test says we have a series and we're looking at that from 1 to infinity of some function a sub n. These terms are this series is non-negative terms, and it converges if and only if the partial sums are bounded from above. So they're closing in on a number, but there's a boundary. All right, so I'm going to go ahead and write this, what I just said. So we can write if and only if like this. And if and only if means it works both ways. All right, so let's look at the harmonic series. So the harmonic series is 1 over n, the summation of the numbers 1 over n, and we're going n equals 1 to infinity. So we know when we write this sum out, it looks like 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus blah, 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 1 over n, and we just keep going. All right, so when we look at this, well, we know like these first two terms we get 1.5. And if I add these two terms together, I get, what is that, 7 over 12. And that is bigger than like 1/2. And if I keep going, like I add 1/5, 1/6, 1/7, 1/8, that's more than adding 4 1/8s together. So it's not converging, it's actually diverging. Now, listen, this thing is barely divergent. You have to do like 178 million, and I'm not making that up, 178 million terms to actually look at this, like look at it and see, hey, this diverges. It's barely divergent. And in fact, if you look at 1 over n, to the 1.8 zeros, 6, 8. If you look at that, it actually converges, which is crazy. But the harmonic series is divergent. So the partial sums are not bounded, it diverges. So that doesn't, the limit, if we look at the limit as n approaches infinity of 1 over n, we know that's equal to 0. That does not imply convergence. It's not an if and only if statement, right? So just because the limit is 0 doesn't mean it converges. What that theorem says is if a series is convergent, then this goes to 0. So that we can't use that either. All right, so let's look at another one. Let's look at the integral test. So if you see a harmonic series, we know it's divergent. That's where I'm going with that. All right. So let's look at the integral test. So we have, for the integral test, we'll have a sequence of terms, and the function has to be continuous, positive, and decreasing. All right. So if that's true, then we can look at the sum and we can look at the integral, and if both of those converge, then, they will either both converge or they will both diverge. They're not, like one's not going to do something else. All right, so here's the integral test. I'm going to look at that with 1 over n squared. All right, so that would be, I'm just going to write out a few terms. So 1 over 1 is 1, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus 1 over 5 squared, plus 1 over 6 squared, and blah, 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 1 over n squared, plus we just keep going. All right, so let's look at this. So let's look at the integral. So the question is the integral from 1 to n of 1 over x squared dx less than the integral from 1 to infinity of 1 over x squared dx? All right, so here's what I did. I looked at the graph and I thought about like right-hand rectangles. So when I look at the area under the curve of right-hand rectangles, so this is 1, and then 2, and then 3, and so on. All right, and I look at the area of the rectangles. I know like I would have f of 1, so the y value times the width, plus f of 2, y value times the width, plus f of 3, y value times the width. And we could just keep going to f of n times 1. All right, so if I look at my picture, I know this summation from n equals 1 to infinity of 1 over n squared is below the graph of the integral from, so oh, that's supposed to be integral. I was thinking about explaining this. 1 to infinity 1 over x squared dx. So this sum is going to be 1, and that's less than 1 plus 1, so 1 is less than 2, so that makes that true. And you can see that the right-hand rectangles are an underestimation, so we can kind of look at it. I added this f of 1 because this integral I started from 1 to infinity, so I missed out on this first rectangle. So I added that first rectangle in here, and that's why that says f of 1. All right, so my using the integral test, I can see that that is convergent. All right, let's look at another one. All right, so let's show that this is called the p-series. And the p-series is, the harmonic series is a member of the p-series, and so is that 1 over n squared. So 1 over n to some power p is 1 over 1 to the p power plus 1 over 2. We just saw that with both of them. So like I said, the harmonic and the 1 over n squared that I just showed you is part of the p-series. 1 over n to the p plus dot, dot, dot. Okay, so we know when p is 1, it diverges. That's a harmonic series. And actually, when p is less than or equal to 1, it diverges. And when p is greater than 1, it converges. So we're going to show both of these. All right, so let's start with it being convergent. First of all, my function has to be positive, continuous, and decreasing. So yes, it is. It's positive, continuous, and decreasing. All right, so you always have to check the function. We need to make sure that that's true first. All right, so I'm looking at this integral from 1 to infinity of 1. Oh, no, I don't want, I'm going to move it up. So p x to the negative p dx. All right, so I know from previous work that we're going to change this to the limit as b approaches infinity of the integral of 1 to b x to the negative p dx. All right, so I'm going to go ahead and integrate this. So I go up one on my power, divide by my new power. All right, so limit as b approaches infinity of, I'm going to go ahead and move this out. And you can write this as 1 minus p also, I don't care. And I'm going to evaluate this. So I have 1 over, wait, I didn't write it that way. I'm just going to go ahead and put b in for x. So b, that looks like a negative. Stop it. Okay, so b to the negative p plus 1, and then minus, when I plug in 1 here, I'm going to get to the 0 power, so that's just minus 1. All right, so now I'm going to go ahead and move this out. So I have 1 minus p, the limit as b goes to infinity of b to the negative p plus 1 plus 1. All right, or sorry, minus 1. Let's go ahead and plug in my limit. So I'm going to go ahead and let b go to infinity. When b goes to infinity, this is going to go to 0 because this is actually 1 over b to the p minus 1. When I move this back, when I move my base back down to the bottom of the fraction. And so when I let b go to infinity, this is going to go to 0. So I'm left with negative 1 over 1 minus p times negative 1, which is 1 over, I'm just going to flip these around, p minus 1. All right, so when p is greater than 1, this thing converges because this is just a constant, right? And so we don't know what it converges to. We just know that it converges. So whatever p is, it's going to converge to 1 over. So if p is 5, it's going to converge to 1/4. If p is 27, it's going to converge to 1 over 26. All right, so we know that. All right, so what about when p is less than or equal to 1? Or when p is between 0 and 1 or equal to 1, right? Okay, so that means 1 minus p is positive. It's bigger than 0. So I'm not going to do that whole thing again because like the limit and integration is all the same. So I'm just going to use what we have up there. I'm going to use the limit as b goes to infinity of, that's a positive infinity, I know it drug out there, of 1 over 1 minus p, 1 over b to the p minus 1 minus 1. All right, so I just took that from up here, so right there in that spot. All right, so I get 1 over 1 minus p. I still have the limit as b goes to infinity of 1 over b to the p minus 1 minus 1. Okay, now let's think about this. Let's talk about this one. If p is between 0 and 1, this is going to get bigger. If p is 1, this is undefined. So let's just talk about when it's between 0 and 1. We already know when it's 1, it diverges. That's harmonic. So this is going to keep getting bigger. This is also going to infinity as p, because p is between 0 and 1. So like think about if p is a half. Right, so then, and b goes to infinity. So if p is a half, b goes to infinity, that's flipping it back up because I'll end up with an exponent that's negative, which is going to flip my base back up to the top, and my base is getting bigger and bigger, so that's going to infinity. So this diverges. So with the p series, if p is bigger than 1, it's going to converge. And if p is between 0 and 1, it's going to diverge. Again, we don't know what it converges to when we say, oh yeah, we get 1/25 here. it converges. It doesn't mean it converges to 1/25. We just ran a test to show that it would converge. All right, that's not the sum. Okay, so let's look at this example. Let's look at n equals 1 to infinity, 1 over n squared plus 1. So first I look at my function. Is 1 over n squared, is it a positive function, so are all my y values above the x-axis? Yes, so you could graph this and look at it. That's what I did. Is it continuous? Yes, because there aren't any values of n that I would plug in that would cause an issue. And then, is it decreasing? And it is decreasing. All right, so yes on that. All right, so let's check this out. We're going from 1 to infinity, 1 over x squared plus 1 dx. And now I'm going to change this to the limit as b goes to infinity of 1 to b, 1 over x squared plus 1 dx. And you're probably already thinking, oh, this is tangent inverse or arctangent. It is. Limit as b goes to infinity of tangent inverse of x, and I'm evaluating that from 1 to b. All right, so I'm going to plug in b. So I have tangent inverse of b minus tangent inverse of 1, and I have the limit as b approaches infinity over here. All right, so this is asking, so really when I plug in b, I have, or when I plug in infinity, tangent, where is tangent inverse infinity? And where is tangent inverse 1? All right, so this is really saying what angle on the unit circle or on my calculator gives me undefined here. So where do I have vertical asymptotes and tangent just takes off to positive infinity. And then for what angle is tangent 1? All right, well, I know tangent's undefined at pi over 2 because tangent's y over x and cosine is 0 at pi over 2. And tangent is 1 at pi over 4. And so this is pi over 4, which means it converges. We don't know what it converges to. We just know that it converges. All right, so last thing is error estimation. And so when we look at error estimation, we can look at like right-hand rectangles and left-hand rectangles. So a lower bound, because this is a decreasing function, we can look at a lower bound and an upper bound, and we can subtract those. All right, so that's basically it on error estimation. So R is like the remainder of the error estimation. And so what that says is my remainder or my error is between an upper estimation and a lower estimation. All right, so we will look at this with, and you can try it if you want to, 1 over n squared. And we're going to use our bounds and n equals 10. So I'll just kind of set it up and show you what I did, and you can try it. I think this is an example out of the book, so you can also look in the book. So I went from n to infinity of 1 over x squared dx. And actually you can use this for both, because what you're going to do, since my bound is 10, I'm looking at the sum of the first 10 plus 1 over 11, because this is n plus 1, and I want r sub 10 to be between this and just s sub 10 plus 1 over 10. All right, so that's kind of what we're looking at there, and then you can check it out on your own if you want to. I got this to be 1.6407, I rounded there, and 1.6498, And then I found the midpoint between these two because that gives you kind of a good approximation of the sum. So you can check that out, and I will see you guys soon.